Cool. So welcome, everybody, to Spark Summit East and the training day that we're doing today. Today's class is Exploring Wikipedia with Spark 2. If you are not here for that class, this is your last chance. Cool. So hopefully everyone's managed to log into the Databricks environment and connected to this document. That's the first thing I'll do here is quickly just highlight a couple of points from this tiny URL link, which is a Google Doc that we want you all to go to. So if you take a look at this thing, let me blow it up a little bit. We call this the student reference sheet, and it's kind of the base point for everything in the class. We want you to bookmark it. So again, if you haven't gotten that tiny URL link yet, you can see it right here. It's pretty easy. SSE Wiki 02, all caps. But this is going to contain this is the base point for all the information that you might need throughout the day, except for that login, which you have on a little card that our TAs have been passing around. So I just want to highlight a couple of important things in here. The first is this getting help section. So first point of contact should be our TAs in the back, Bill, Kyle, and Miles. Can you guys wave, do a little thing? Back of the room there. Feel free to shoot your hand up if you're having problems. You can run back to them. They'll be circulating as well. Barring that, in terms of the environment cluster issues that we're getting into, these clusters have been pre-spun up for you, so you shouldn't have to worry too much about this. And as I understand, that's all gone successfully. But any issues there, you can also shoot an email over to trainingsupport@databricks.com. The next thing, and this is buried a little bit, but it's right here, is the Q&A document. So this is another one that you're probably going to want to have up. And this is for curriculum-based questions. As we're going through, this is a really fast-paced thing. So if you have any questions that are a bit off topic, you want to learn more about something, I just don't have time to answer them up front. Barring asking the TAs, you can also put questions asynchronously here onto this Google Doc. So what you would do is you can put your name or not if you don't want to. I'll start one out here. Question from Christian, and then maybe I'd write something. This is a sample question. I am very curious. And one of the TAs will be able to get back to you, and then we'll highlight some of the most interesting questions from this document throughout the day. So keep that Q&A document in mind as well. Again, just linked out from right here in the student reference sheet. Moving along, later in the day, we are going to need to go back to this document for these Maven coordinates to import a library that's not in Spark. We'll get back to that a little bit later in the afternoon. And last but not least, you can see here a tentative schedule of some of the modules that I'm planning to go through. As the day progresses, we will probably change this up depending on what you all are interested in, what we go quickly on, what we move slowly on. But this is the tentative outline, just kind of going into this thing. Cool. So,
hey, Christian,
yep.
Do you mind scrolling back up to the tiny URL?
Sure.
Grab that?
So I've been asked to scroll back up to the tiny URL. Here that is again. Spend 15 seconds here, snap a picture if you don't want to type it in, but really just type that in. Cool. All right. So let's see. I've introduced the TAs. I've introduced the class document. I'll introduce myself briefly. My name is Christian Viscardi. I am an instructor here at Databricks. I've been working with Databricks as an instructor for about 9 months now, and it's sort of a contractor type of role. My full-time day job is working with another data science training organization, the Data Incubator. We do not just Spark, but also a wide variety of other data science machine learning topics. That's me. And now let me bring up some more slides to introduce the course and just clarify what today's learning objectives are. So I'm going to pull this out. Come on. Oh, yeah, I can just do this. Cool. So here's what we're trying to get through today. Basically, help you guys learn enough to be dangerous with Spark. We're going to be going pretty fast-paced, but this is meant to be a high-level overview of a number of the different APIs in Spark, the idea being that once you've seen all this, you can dive deeper into whatever aspects of the Spark ecosystem interest you and set up whatever crazy cool pipelines for that. So we'll be doing some hands-on with the APIs, a bit of overview of the architecture, as well as some dives into the UI, performance optimization, tweaking, and some demos, again, of those really extensible APIs. Cool. And the last thing I wanted to introduce before we get into it is you all. So where's my mouse here? We did have a pre-class survey go out, so thanks to those of you who filled that out. Looks like we got 26 responses, and this class, as I understand, is about 70. Later in the day, we'll have a post-class survey that we'd really like all of you to fill out. Your feedback's super important to us. But here's the pre-class survey. So you can see in terms of what the class is interested in here, there's a good bit of interest in the core Spark functionality, so we'll definitely be spending a big chunk of time this morning on that. As well as Spark streaming and MLlib in particular, as far as some of those other sort of libraries built on top of Spark go. Not as much interest in GraphX. We will do a brief demo of that because I know there are some of you in the room who are curious about that. But you can kind of see the main focuses that I'm going to try to make today. As far as programming languages in the room, we see that many of you are comfortable with Scala and Java. We also have some people who are a bit more comfortable in Python. So as we'll see momentarily with the notebooks, you can actually run the vast majority of the content that we're going to be doing today, either in PySpark or in Scala Spark. I will be mostly demoing in Scala Spark, but as we'll see in just a second, the Python API and the Scala API, especially in the data frames, data sets world, which is what we're going to be using today, they line up very closely. What else was interesting here? Some of the focus on the class. So it looked like a lot of you were planning to sort of develop proof of concepts after this, and development seems to be the biggest goal, as well as some of the architecture, UI, investigative type of concerns. When you're actually running jobs, how do we tweak them, make sure performance is as good as possible on the cluster that we're using. Cool, and then here we go. As for Spark experience, you can see, apologies for the pie chart, it's a Google Docs summary thing, but you can see here that for the most part, we have people who have played around with Spark a bit, as well as some more advanced people in there. And then, yeah, the proof of concept. So a good mix of people in here, some reasonable familiarity with other big data technologies in the ecosystem. And not too many of you have been to a training, which is great. This is going to be all new, all fun. Cool. All right. So I think without further ado, let's get to it. As you probably saw in the description, a large portion of this class is interactive, and we're going to be working inside of Databricks' interactive environment. I've lost my mouse again. There it is. So hopefully you've all managed to log in there. And I'm going to bring up my version of the same thing, put that back in. Cool. So once you've logged in, you should see a screen approximately similar to this one. Is that a reasonable size in the back? Cool. So now what we're going to do is click on that home directory, and hopefully you can follow along here. And we're going to get to some of these notebooks. So once you click on the home directory, you'll see that we kind of expand our directory structure here. The most important thing for us is going to be this SSE 2017 folder. So you click on that, open it up, and you'll see that actually the data science materials are here on your cluster as well. But we are exploring Wikipedia with Spark today. So we actually don't really need to do much workspace preparation. You can kind of see once you click into that folder that that's the first thing that's all been done for you by the Databricks team. But what we will want to click into is this overview document, or excuse me, this overview notebook here. And we're going to start running stuff from that and talking from it. So right before we get into this, any questions on anything I've just talked about? Great. Okay. The purpose of this notebook is really to just outline, number one, the data set we're working with, and number two, give you a brief overview of what's going on in Spark and some introduction to that ecosystem. So Wikipedia, I think we're all reasonably familiar with Wikipedia. World's largest online free encyclopedia, 5 million plus English articles, 38 plus million articles in other languages. So in terms of the data that we get from Wikipedia, and we'll be actually looking at on Wikipedia today, we'll be looking at some subset of English Wikipedia for the most part. You can see that the sort of full text of English Wikipedia is about 54 gigabytes in size. For us, we're going to be looking at a smaller couple gig subset of that. That's not the only data that Wikipedia is going to provide us, though. We also get clickstream data. Clicking through page by page, what user activity actually looks like. We're going to get edit data, live edit data, so we get a stream of people who are editing documents in real time. That's going to be really interesting as we look through Spark streaming and want some live data to actually play around with. And then we have traffic data as well, activity data that follows, what pages are being accessed right now. That's another live stream that we actually get, which is nice. What pages have been accessed in the past 24 hours or other time frame. That data is all logged by Wikipedia. So there's a really rich source of open data here that presents us with a lot of relevant use cases, right? I think hopefully all of you have heard something in there that would be relevant to what you're doing at your job, whether that's clickstream data, whether that's sort of edit logging data, whether that's traffic data, or just sort of the full text kind of NLP stuff. That's all really interesting to look at. So we'll play around with all that and get a bunch of different views and insights into this really big data set. So Spark. I guess first question here, show of hands. Who has played around with Spark before in the room? I know we asked it on the survey. Cool. And for those of you who have, who was on Spark 1.6? And then Spark 2? Okay, cool. So there's a good mix in the room, but it looks like a decent number of you have actually already played around with Spark 2, which is great. So that's really good to know. You're then kind of familiar probably with some of this background. The latest stable release here is Spark 2. Spark itself kind of came out of Berkeley as the next evolution of the Hadoop MapReduce framework and world. The idea being we don't want just data locality where we're running computations on the disk of the same machine that we care about. We also want to put stuff into memory, right, and take advantage of the large amounts of RAM and memory that our clusters have, and that's getting cheaper and cheaper. As well as, of course, the super nice unified APIs that we get from Spark that make developing a lot easier. Here's another one. Show of hands. Who's written a MapReduce job before? Yeah, a few of you. It's not fun, and I think you'd all agree that Spark is a lot easier to write, debug, work with, and all that. Cool. So Spark has any number of different APIs and views. The core one that we're going to be looking at today is this data frames SQL API. For those of you who have just played around with Spark 2, you might also know this as data sets. Data frames and data sets are nearly identical up to some typing, and we'll see that the interfaces there are very familiar. If you have used Spark 1.6, it's not going to be very different as we work through. And then we have these other libraries kind of sitting on top of those core data frames. The graph analysis library, which is called graph frames. The Spark ML is the data frame version of machine learning, as well as Spark streaming. So right now, there are two versions of Spark streaming. One of them is for data frames. That's called Spark structured streaming, and that's a bit newer. We're going to demo it later in the afternoon, but it's not quite as stable yet as the old RDD-based Spark streaming. So we'll spend a little bit of time looking at both of those streaming APIs. Actually, for these other two, we'll be taking a look at the interfaces specifically in data frames, which is the world we're kind of moving towards. Yep. So one of the big goals of Spark here is again to kind of provide us with a nice, clean, unified interface where we don't really care what cluster we're running on. We can use Yarn, that's pretty popular in industry. Mesos is not a huge problem either. Kubernetes will work in terms of linking up some Docker containers. Then we can really run in a bunch of different environments depending on what's available to us. We can also really link up to a ton of data sources, and this is one of my favorite and I think one of the most powerful features in Spark. If we already have a Hive cluster set up and running, we can connect into our Hive tables. We can load up JSON CSV parsing, and actually for those of you who've used Spark 1.6 and this sort of thing, we'll see that some of the parsing functionality in Spark 2 is built in and really nice. Previously you had to import a Databricks type library, or a library that was developed by Databricks in order to parse CSVs and JSON cleanly. That's all nicely done for us now. We support Orc and then Parquet, which is really a fantastic format. Show of hands, who's heard of or used Parquet before? Awesome. Okay, cool. Glad we're familiar with that, because that's what we're going to be using a lot of today, and it's a really fantastic serialization format. So in any event, one single Spark job can plug in from any number of these data sources, right? And unify, combine them all into one sort of holistic analysis, which is really, really cool. Cool. Yeah, so as mentioned, we're going to spend most of today, as far as core interfaces go, looking at the data frames, Spark SQL datasets interface here. However, the original thing that all this is built on top of is called RDDs, redundant distributed datasets, or resilient distributed datasets? Yes. In any event, that's a bit lower level. You write a lot of sort of functional programming Scala-y constructs there, and that is just a lower level API that we're not going to focus on as much today. But it will be necessary for some of the Spark streaming stuff going forward if you're not using structured streaming. Cool. So a brief overview here of the architecture that we see in Spark. So the way things are set up, right, is that typically we're running Spark on a cluster, and that cluster will have some sort of master node and then worker nodes, right? So when we think about the JVM that is orchestrating our Spark code, we think about a driver instance, or a driver JVM. So that's sort of a separate concept from the master, and we try to not conflate those terms as much as possible. But this is in some ways kind of it's the orchestrator, right? This JVM is actually what we're going to be sort of interacting with. You can kind of sometimes think of it as your laptop or this notebook interface that then sends out work and tasks to our executors, which are going to be either different nodes across our cluster, or possibly we could have multiple JVMs on the same node. But each executor is basically its own JVM that has some number of cores allocated to it that it can run tasks on. So there's a diagram of that. So the driver is kind of sending out tasks here to some of the executors, and those slots are getting filled up with work. So of course the goal here is, and one of the big things that we're going to talk about in Spark tuning is partitioning our data to make sure that we don't have a diagram like this, but instead we have every single one of these empty slots filled up with work, right? We want to always be maximally utilizing our cluster, maximally utilizing all the I/O bandwidth we have, that sort of thing. So as far as the particular architecture here, we are running what's called Spark Standalone. If you've played around with Spark on your laptop before, installed it, that's what you'll have been running as well, where the driver and the executors actually all live in one big JVM with a number of cores basically simulating separate executor tasks. So that's all living on an EC2 instance, and this is more than enough for the small work demonstration purposes that we're going to be doing today. But this is kind of what things look like here, and then of course the notebooks here are actually connecting into that via a sort of like kernel-y WebSocket API setup. Cool. Any questions on that the 1,000 feet overview of Spark? Sure.
So, any specific reason for selecting 3.7 gig for the GPU? Any calibrations?
Yeah, so the data sets that we've provided are all, it's 3.7 gigabytes of memory for the executors total. So once we fill up that RAM, we can still actually write back out to disk. But in the case of the data sets we provided, we're going to be able to keep everything in RAM. Cool. Okay, so moving forward, here's what we're going to see. There are 3 different types of notebooks in this course. There are notebooks for data analysts, so that's going to be a lot of the data frame SQL stuff with visualizations. There are going to be some notebooks for data engineers, the more deep divey, let's take a look at exactly how this is running, how can we get a better view into our jobs, how can we debug these things, and how can we tune them. And then data scientists, let's take a look at some machine learning. Let's take a look at some more complex higher level algorithms. So some of the graph frames and machine learning stuff is going to be focused towards data scientists in this class. So another show of hands type thing. Who here would classify themselves as a data analyst? Couple. Then data engineer. Cool, a bunch of us in the room. And then data scientist. Okay, cool. That sounds about right, kind of based on what I was seeing in the surveys. So you can actually, I'll show this off right now. If you click over into the workspace, you can see that we've prefixed the different notebooks. These ones here are all sort of Spark 2.0 overview stuff that we won't go through because it sounds like a decent number of you kind of just started on Spark 2.0 or are already playing around with that. If we have time at the end and there's some interest, we can look at those. But the majority of the content here lives in, as you can see, this one's prefixed with DE. That's for data engineers. DS is for data scientists. And then if you click into either Python or Scala here, I'll click into Scala, you'll see that there's some prefixed with DA as well. And that's for the data analyst type of notebooks. We won't be able to get through all these notebooks today, but feel free to export this, create your own community edition cluster on Databricks, and continue exploring this stuff after the class, because there is a lot of content here, and we have until 5 p.m. to sort of work our way through some of it. While we're here, you will also see that there is a Scala folder as well as a Python folder. So who here is would be more comfortable in Scala? Raise your hand. And then who here would be more comfortable in Python? Cool. So yeah, it looks to be about 2/3, 1/3. For that reason, I'll probably stick to going through things in Scala. But for those of you who did just raise your hand for Python, almost all of the content here is identical. And actually, the only notebooks where there isn't a notebook for each language all live in this outer context. And we'll see that those have some Python and Scala cells some running in Python, some running in Scala. But for what you're looking at, you should pick whichever language is more comfortable to you. Again, I'll be demoing in Scala, but these Python notebooks are identical or nearly identical and just as good. So we can actually highlight that below. And so for those of you who have not tried this yet, what we want to do is make sure everything's working by running and actually executing a cell here. So let's take care of that. So the first thing I'll point out is I actually already executed this one. Can I clear the output here? Goodbye, output. OK, so you'll see a blank screen like this. And you'll see here, actually, there is one cell here and then another one below. You'll notice that at the top of this notebook cell, we've got a little %Python thing. This is actually telling us that this cell is going to be run in Python, even though we can see up here this notebook is mostly Scala. So you can see here, in case you were kind of wondering how similar or different those two APIs are on top of Spark, that really the Scala and the Python API look quite similar, and it's going to be no trouble at all to follow along in Python. So don't worry too much there. And now let's all run whichever cell we're more comfortable in, or the cell for whichever language we're more comfortable in, to make sure that everything's working. So you can do that just by hitting Shift and then Enter. You'll see a message like this pop up, and you just want to click Attach and Run. So the way this is set up with the Databricks environment, right, is all these files kind of live in a separate, I assume it's like an EBS type of deal. There's an EBS block on AWS here where all of your data is actually living. And that, when we attach to a cluster, gets mounted in to that cluster in order to be executed. So again, the Databricks people spun up all these clusters for us early in the morning. And they're all good to go. So you'll just see that attach button, click it, and it might take yours a little bit longer because I had run this a few minutes ago. But you should see some output like this come up. And you can see here as well, this is some of our first Spark code, so I'll just talk through it for a moment here. For those of you who use Spark 1.6, this is going to look a little bit different. You used to invoke something like this .read.parquet option from the SQL context, right? We now use Spark, so we will see SQL context peppered in here a couple times, but for the most part, the main interface to our Spark context is no longer SC in Spark 2, but it's Spark. So for the Spark 2 people, that's old hat. You're already comfortable with this, but this is one of the new and improved things inside of Spark 2. So we're then going to read in some data. It is Parquet data, so we have some metadata, we have some structure there. It sounds like a number of people are familiar with Parquet, so that's great. So we'll pull in that columnar data, and that's a pretty quick operation because it's in Parquet. That will then order it by the number of requests that we've gotten, and then say, let's show 50 of those. And then this display built-in, for those of you who have used Spark but have not used Databricks, this display built-in is a just nice little piece of infrastructure that Databricks gives us that allows us to present a nice tabular display here that we can go through of the data that we're looking at. So you can see here, just to look through some of these fields, that we're looking sort of at EN, which is going to be English Wikipedia. That's the project field in this article data set. We'll get the title here in the article column. Then we have the number of requests to that particular article or page. So you can see the main page really gets hit a lot here. And then it looks like this byte serve column is not giving us any particularly interesting information. But yeah, this is kind of the most basic data ingestion that we could possibly do. Cool. So any questions, comments, or concerns there? Yep.
So this file, where does it exist? I don't know where the file physically is.
Oh, just where this file lives?
Yeah, the Wikipedia in one.
Or you're saying that your cluster is not finding the staging? Oh, sure. Where is that file? So we'll see in the next notebook or two that there's actually a way to kind of poke around the file system that we're looking at. It's on an EBS block, kind of in your local file system here. So we actually mounted all this stuff in via a script earlier. And if you're curious about how that looks kind of in the Databricks world, Databricks interface, you can actually take a look at this datasets mount script that's right here, and that did that for you.
And what is that part? I don't know what that is.
Parquet? Parquet is a particular data format that's very popular in kind of like distributed computing circles. And what's really nice about it is it's columnar and stores metadata outside of the file itself. So we can actually just load up particular columns that we're interested in without looking at the rest of the file, via some clever offset tricks. Or we can even just load up particular rows from the file. It's easily chunkable and distributable out to a bunch of machines, and is really, really fast in terms of the serialization and compression that they used. So just a really nice file format that I'd recommend looking into if you plan on doing kind of more of this stuff. Cool. And yeah, any other particular technical concerns, feel free to grab the TAs. All right, great. So with that all covered, the overview kind of taken care of, let's move into actually looking at some of this stuff and looking at the Wikipedia data set. So what I'm going to do is, yeah, I think this should be all right. Open up this O1 DA page counts notebook. And again, got to that just from clicking on the workspace, exploring Wikipedia, Scala O1. If you want to open it in Python, feel free. The same notebook is in there in Python as well. So the data set we're going to be looking at here is some of that traffic data. So the past hour in, I think, like February of 2015 approximately, of traffic to all of English Wikipedia, how many people looked at each page, and some more kind of traffic information there. So this is a data analyst-y one. We have a bunch of business questions, and hopefully this should just get us more familiar with that interface. For a lot of you, I suspect this is going to be a bit of review, but it's good to go through to make sure we're all kind of on the same page there. So we're going to check out, again, just some of the unique counts of pages that were actually visited. So, there's a question, what percentage of Wikipedia actually gets visited in a given time frame, right? You'd think there's so many random Wikipedia topics out there, probably only some subset is actually viewed in the past hour. What's that actual number? And then how much traffic did each of those, first of all, just like a global traffic count, how much traffic are we looking at in terms of English Wikipedia? Some of the most popular articles that get viewed in a given hour. A little question about our own favorite technology here, Spark. And kind of moving on, asking some more questions along those lines. We also stratify here by desktop and mobile traffic, which we'll see is very easy to do and kind of an interesting question to ask of this data. So those are some of the questions that we're going to ask of this data set. As far as what we're going to do, again, we're going to get our hands a little bit dirty, right? We're going to make a data frame here by reading in some more data. We're going to take a look at the schema of that and then talk about what that means. We'll do some simple transformations on our data frame using the data frames API in particular, as well as take a look at some important actions, some of the really core ones there, just counting up stuff and showing it. Cool. So again, this is just sort of a high-level overview here of what the Wikipedia data set's going to look like and what the data that we're actually getting in resembles. So we have it in a bit more structured of a format here, but you can kind of see we have the project name, the title of the page, the number of requests, and how much content was returned. So I think we either stripped this out or there was a bug in the reporting when we actually looked at this data set, as you could see in the previous notebook. But there's a whole bunch of prefixing that's going on that you can see there that's sort of interesting. The first thing is, again, just the Wikipedia, or excuse me, the Wikimedia project name. Again, this is the whole Wikimedia project, I suppose, and not just Wikipedia. But we can see that we can actually also filter out to mobile with the .mw extension that we see there. N.d is going to be desktop, that sort of thing. Cool. Here, you know what? This is actually a little bit hard for me to read down here. So what I'm going to do is change up my settings quickly. We're going to just mirror the displays here. There we go. Cool. Is that a reasonable size? Great. Okay. Yeah. So we can basically just break down based on these prefixes what the different Wikimedia projects we're looking at. Mainly, really, what we're going to care about is the ones without any extra extension there, which is just the EN English Wikipedia articles. But we can look through kind of the rest of this Wikimedia project by taking a look at some of these extensions. Cool. So you guys were asking about how the file system kind of looks here. So this whole first cell that we're going to run here is a bunch of Databricks specific stuff, but you can kind of get a feel for the directory structure that we're looking at here. So what we do is call this DB utils, that's going to be Databricks utils, and take a look at the file system that we've mounted up. We can display that after attaching and running to our cluster. And so all we're doing here is you can just kind of see the different chunks of the file that we have in our file system here. Notably, again, kind of nice is that we have metadata, common metadata. These are our Parquet metadata files that we will be able to use when we're loading in the data to not actually scan the data to get a feel for its structure, but instead just take a look at some of the metadata that Parquet gives us for free. So that's kind of really nice. So once again, we're going to follow this same flow we were just looking at the end of that first notebook there. We are instantiating a data frame here. For those of you who haven't seen so much Scala, hopefully I think this is pretty clear, right? In Python, it's going to be almost identical, maybe modulo that val, which is kind of awesome in terms of unified interfaces. So we run this cell, shift enter, again is the command to do that. And you'll see that took about 3 seconds. Again, that's because of this Parquet metadata. We don't actually have to scan through this file, even though we can see here, if you kind of look through this output, that we have our schema already loaded. We see that the project name is a string, the article name is a string, and so on and so forth. This only took a couple of seconds because we did not actually need to scan through that data to get to know the schema beforehand. So Previously, we used the Databricks display built-in. If you're not in a Databricks environment, if you're in a Spark shell, something like this, you can use the .show function just to get a look at some of the first few records that we actually loaded up. A little aside here that's kind of interesting is that with Parquet, we actually didn't load up some interesting results given back to us. Live Wikipedia, right? This is what happens when you use live data in a talk. But in any event, what's kind of cool is we saw in the file system lookup above that there are any number of different Parquet parts here, right? We've got, it looks like we chunked this into 5 or 6 or 7 parts. We actually only looked at the first few rows in the first part to pull this back. So in terms of the file we need to look at, or the portion of the file that we need to look at, it's really, really small because of what Parquet is letting us have. So that's enough about that. So then, again, we kind of saw this in the above output. Oh, sure, there's a question?
So in your result, it says job is 5 and mine says job is 8.
In,
In
oh, sure. Yes. Sure. Yeah, thanks for letting me know that. I will repeat questions. So the question is up here. It says job 5 in my output. In your output, it's going to give a slightly different number. That's totally fine. I think it's probably because I had run an extra job or two just a few minutes before class started that you hadn't run. But you don't need to worry about the particular job numbers that we're seeing here. Those are just numbered based on the number of jobs that we've run in our cluster, right? Sure. Question?
So when you created the data frame,
Mm-hmm.
you mentioned that it took 3 seconds because you just had to look at the metadata, right?
Yep.
But isn't that like a transformation and not an action, and it won't really do anything at that point in time?
Yes, that's a good question, and we'll get a little bit more into transformations versus actions in a second. But so the question was, it took 3 seconds to load up this data, right? Isn't that something that's a transformation? For those of you who are familiar with transformations versus actions, isn't that something that's lazily done? And the answer is yes, typically. We'll see that when we actually use the data frames API, we are able to, in Spark 2.0, infer the schema. And for some file formats, that involves actually scanning through the files through our data set when we're calling this spark.read. So there will be a bit of scanning that happens, even though, yes, this is technically a transformation. However, yes, in the case of Parquet, we just look at the metadata file. All that schema information is already present for us. So we kind of get it for free, right? And that's how this continues to look very quick as sort of like a lazy type transformation. So moving right along, and again, feel free to put any more questions in the document as well. We then take a look at that schema and just see what our columns look like. We can see here that this print schema function gives us a nice little table. We have, as we saw above, we keep mostly English Wikipedia in the data set that we have here. We then have the article title. Both of those are strings. You'll also see this nullable equals true field. That means that, of course, we can have null values in this column. Then we have an integer field here, the number of requests, and a long field for the number of bytes that actually are being served from each page. And again, all of those are nullable. We can have null values, and we have some nice typing here inside of our data frame. Cool. So in the data frame world, there's a very easy way to count things up. And we'll actually see the count action used in a number of different situations, including for caching and this sort of thing. It's like an easy way to actually parse through our data set in some instances. But we call this count action here just to get a sense of how many records live inside of the data frame that we just loaded up. Again, because we're using Parquet metadata, this is actually an action that pulls from the metadata rather than actually scanning through our data set. Again, Parquet keeps some notion of how many rows it's actually holding inside of its chunks. So that's why, again, this only takes 2 seconds versus some of the counts we're going to see later on different file formats that take a bit longer.
Question. The schema isn't derived from the data set that
Yes, so the question is the schema derived from the data set? And yes, it is. That was determined at some point. Whenever this Parquet file was created, there was a schema that had been placed on it. So when we wrote out to Parquet, it not only saves off the data onto disk, but it also saves this metadata, which includes schema information for us when we pull it back in. Cool. So with some really basic information about our data set, we see we have about 2.3 million articles we're looking at in terms of an hour's worth of traffic. So that's already kind of an interesting point, right? Let's take a look at just how many different projects across the English Wikimedia sphere saw traffic. So what we're doing here is taking a look at the project column using just a typical select statement. And you can see this is very SQL-like, and we'll talk about the SQL API and how these are actually both interfaces onto the same low-level engine. And you can write these queries in SQL as well, which is kind of nice. But here we're doing it just to show off the data frames API. We're selecting out that project column. We're then doing just a distinct on all the values inside of that column so we can get a feel for the number of distinct Wikipedia projects that receive traffic. So after we do the distinct, we then call show to actually pull those values back to us. And we can see here that a number of different projects were returned. We only are showing the top 20 rows here by default when we do a show. You can actually change that parameter by doing something like .show. If I only wanted to see the top 5 rows, oops, there we go. You can do that. If I wanted to see the 100 rows, I could do .show 100. And that was actually the first challenge. Well, in any event, let's do that here. So let's show off 50 lines. So we'll just walk through this one together. The easiest way as you scroll down to solve this first challenge is probably just going to be to copy and paste out this show here. Paste it into this cell. And we are meant to display 50 lines. So let's just change this number to 50. And hit enter, and there we go. We've got 50 rows being displayed, or up to 50 rows being displayed. You can see here that it looks like there might be slightly fewer than 50 rows total that actually, or slightly fewer than 50 Wikimedia projects that saw traffic in the past hour. Cool. So given that we've gotten a feel for some of the distinct Wikimedia projects, let's suppose we do want to see exactly how many distinct ones were there. We can change this show to a count. Oops. Hit enter there. Yep, and we'll see that 24 distinct Wikimedia projects saw traffic in this hour. So in terms of the breadth of the different Wikimedia universes that do see traffic, we're going to get a feeling that most of those 2 million unique article hits are going to be from Wikipedia, right? That's what most people go to. That's what I think about when I think about the whole Wikimedia project. Cool. So let's take a minute here. We'll take 2 to 3 minutes just to think about this second question here. Can you figure out how to show 10 articles that saw traffic during that hour? So again, this should be a review from mostly everybody, but let's just take a minute to think about it. All right. So did anyone write the code? Does anyone want to share the answer that they typed in for that? Who typed something in? Show of hands. Cool. Who's checking their email? Yeah, so I think the easiest way to do this, or sort of what we're looking for, is you can just select out the article column here and show 10 of those. Notably, this is probably a good time to talk about this $sign or introduce that. Basically, what this $sign is doing is it's a Spark SQL built-in that's allowing us to not just say, hey, this is some string, but this is also actually the particular column we're looking at. So there's a bit of Scala syntactic sugar going on in here, but the idea is from here we'll actually be able to also call some SQL functions. We could select the count of article, for example. Oops. This way, but we'll look plenty more at that later, and that's all a lot easier to do as when we use this $sign in front, though it is not strictly necessary sometimes. But in any event, we select the article column, show 10, and we're just going to see what we saw above. Some of those various article titles, as you can see, they're sorted. So we must have done a sort right before we output this data to Parquet. Okay, so moving right along, how much traffic did each English Wikimedia project get during that hour? So here's a slightly more complex query statement where we're going to select off 2 columns. First of all, the particular projects, and then the number of requests. We can then do a group by on the project, right? So once we do that, we just do a sum on each of those groups, which we can do with this .sum function here. And then we're interested in we're probably going to be most interested in how that distribution looks in terms of which were like the top 10 most popular projects. So we can do that with an order by on our groups. And you can see the .desc function here is making that descending. And then last but not least, we show. And a bit of a segue here that we're going to be talking about transformations and actions in just a minute. But the gist of it is, let's suppose I don't run this. I just got rid of that show call at the very end there. You'll see that took 0.36 seconds to do a select, a group by, a sum, and an order by on a decently sized data set, right? We have what, 1 million rows or 2.3 million rows. So the point here is that these calls are actually all lazy. So those of you who've seen functional programming, this sort of thing before, you're probably familiar with the concept of lazy evaluation. Basically, we are telling Spark ultimately what we want it to do. But Spark will not do anything until we say, hey, actually give me some data back. So if I now paste this show call back in and rerun this cell. Fun aside, if you don't want to scroll down, you can also hit Control-Enter to run cells, much like Jupyter Notebooks, that kind of thing. And it won't immediately bump you down to the next cell, which is kind of useful to know. But then, okay, great. So now we have a result back, number 1. But number 2, this took 5 seconds. So this is a bit more reasonable, right? It took a few seconds for this whole aggregation to actually be run. So what this allows us to do, and again, we'll get more into this as we move along in the course, but this allows us to say, okay, I want all these things done. And then it allows Spark, the SQL engine, and its query planner to go in and say, okay, can we do any optimizations on this query plan to make it a bit faster, right? We can do low-level stuff like say, hey, when I actually load in all this data from our Parquet files, because Parquet is columnar, right? All I'm going to need to do is actually load up the project column and the request column, and I can skip all that other data. So that's an immediate improvement, right? And then these sort of optimizations are enabled by this lazy model of transformations and actions that we have. Cool. So when we actually do that group by and see which projects are the most popular, okay, great. English Wikipedia, the most popular, as expected. Mobile Wikipedia, also very popular. And then we can kind of see this tail even just looking at the numbers here. So we have a bit of a long tail going on as far as other Wikimedia projects and aspects of the Wikimedia universe. But again, this is all very exploratory. We kind of knew this without asking the question, right? Cool. So going along, aside from the lazy evaluation model I was just talking about, we sort of formalize that in Spark into two different sets of operations. Again, transformations. So transformations, as I showed above, are going to be those lazy ones that don't actually cause any data to be loaded, any code to be run, for the most part. Actions are the things that are actually going to cause data to run. So in particular, transformations are going to be operations that act upon a data frame and then give us a data frame back. So what we did up here, right, is we chained together a bunch of transformations. We, first of all, start off with our whole data frame, all the columns, all the rows, everything. We then select a couple of columns. So now we're going to get back, after this line, another data frame with just those two columns. Then after the group by, we're going to get a group by data frame back, right? We keep moving down to call sum. So now we're going to get a new data frame with all those aggregations done for us. And then once we make our order by call here, we get back the last data frame in this chain of calls that we're doing. But we get back that final data frame where it's ordered by how many requests each page saw. And then last but not least, we call this show function, which is just going to return a little table to us. So that's kind of what the transformation action flow looks like. The actions are almost always going to be among the very last steps you do in your data processing, data analysis workflow. Yeah, there's a question in the back.
Does Spark use up memory as though it is creating all those intermediate data frames, or does it have some sort of efficiency?
Yes, great question. So the question is, when we call this transformation, is this data frame going to materialize, and then is this data frame going to materialize, and so on and so forth? And the answer is no. Spark, especially the Spark SQL engine, has a whole query planning optimization structure that will allow us to not necessarily materialize all this and produce some kind of optimized execution flow. And we'll actually take a look at how you can see that query plan at a bunch of different levels in the next notebook. It's all really cool. All right. So we just saw a bunch of transformations here. You can see that here's another list of those. The distinct call we were doing before to get the distinct number or the distinct names of projects. That is also a transformation because it's going to just give us back a small data frame with each of those unique names. Group by, sum, order by, as we were just using, filter. You can see these are all sort of very SQL-like statements. And then some of the actions we've seen so far, show and count. In RDD land, we use collect a lot, which is going to pull back an object or pull back data from the executors to our driver as a Scala object, and we are able to use that in the data frame dataset world as well, I believe. Or take is another similar one to collect. And then last but not least, we have save, which is going to be an action that writes out to files, right? Yeah, there's a question in the back.
So other than save, I
Great question. So the question is, let's suppose I do something like this. I do my aggregation and I show some results to myself. And then afterwards, I want to save this back to disk, right? I just did something interesting that I want to save off to show people later. And what we're actually going to do there is cache the data, or cache this data frame so that we don't have to do what you're describing. That's sort of the default thing. This is one of the most important optimizations in Spark. So what we can actually do here, and we'll get down to this in just a moment, but there is another transformation that's not mentioned there, cache, which doesn't do anything. It gives us back the same data frame, but has the side effect of caching the data frame up to this step in memory so that we can then call different actions on it without rematerializing everything from disk, which would be the default behavior if we didn't call this cache step.
It doesn't do that until show.
Correct. Yep. Yeah, so the comment was that that's not going to happen until show. Cache is also, I would put out here, a transformation. So it is also lazy, and will just cache, as our query is going through, it will just cache at whatever point we tell it to, but only upon the transformation, or excuse me, only upon the action being called and data actually being materialized and loaded up, right? Because we don't want to cache before that and then start calling stuff again.
Question?
Mm-hmm.
Is there any way to cache by not calling action? Like I just want to cache it before I start doing something.
Sure. So there's a question which is, what if I want to cache data without doing anything? I mentioned that we use the count action in a bunch of different situations. The main one that we're going to see it here a bunch of times is we can actually just use count as kind of a hack to call an action that's not doing too much work and is also loading up our data into memory and making that cache happen. So typically you're going to want to just call a count to get that cache materialized, but you do need to call an action to materialize it. Cool. All right, so we're going to kind of speed through the rest of this so we can start talking about some more of these Spark internals. I think you guys are getting the feel for how this data frame stuff works. So we can also do a filter here, just looking at English Wikipedia. Pretty straightforward. Again, this is a transformation, so nothing actually comes back. And this is returning a data frame, or more specifically a data set, because we're in Spark 2. Data frame is actually an alias for data set in Spark 2. But again, we don't need to worry about that too much, especially you Spark 2 folks. So once we do that, just filtering and looking at English Wikipedia, we can do an order by to just see which pages in English Wikipedia were the most popular. So the main page, wow, a lot of people hit the main page of Wikipedia. We can see there's some of these category prefixes here. So Wikipedia, so even like English Wikipedia is divided into a bunch of different categories. I guess Donald Trump is very popular. 404 page, very popular. This sort of thing. So this was from an hour, I think, in February of 2015 or 2016. So you can see why the political stuff is going to be very popular at that time. As mentioned above, we can make that look a little bit prettier in Databricks. Just instead of calling a show action, we pass in the final data frame that we're interested in displaying to the display function, and then on the back end, Databricks is going to call that action and load it into a nice table for us. Cool. So I think some of this discussion about Wikipedia namespaces, while interesting, is not going to teach us much about Spark. But you can see we're probably going to want to start thinking about filtering out some of these namespaces, right? We're not worried about, like, for example, if we want to see how much traffic the Wikipedia page for Jimmy Wales, founder of Wikipedia, gets, we're not interested in his user page because he's also a user of Wikipedia and an editor. We're interested in the Wikipedia page, the article about him. So I think that's going to motivate our next cells here, which is doing a very hacky sort of filter. Sometimes you got to do stuff like this, as I'm sure we're all familiar with, in order to filter out some of these categories that we're just not as interested in, right? So what we do is we chain together these, I guess, 17 filter actions to get rid of all these different categories. There's a file category, I guess there's a category, there's a user category, a talk category, and so on. So we're going to create this data frame to get rid of those. Just in case you had any doubt in your mind about the transformation versus action thing, you can see that this long list of regular expression filters just, again, took us half a second to run. That's because we're just telling Spark what we want to do, but we're not actually materializing things yet. So now, when I call this display function, this one's going to take a second. And we're only going to see the articles here that are interesting, rather than some of those user and category things that we were seeing before, images, that sort of deal. So again, a lot of political stuff going on here. Cool. So what if we want to look at Apache Spark? And again, we'll just kind of go through this one quickly. So we called this page count, so on and so forth. I'm going to copy and paste and not say that long name. Filter article. You'll notice above that we actually use the triple equals here. This is an operator overriding thing in Scala. So we can't override double equals, I believe. If you're in Python, I think you do see the double equals, but it's just a little quirk. And then we're going to look for the Apache Spark article. And then let's show that. Cool. So we can see in a given hour, 71 different people, or 71 requests. There were at least 71 requests. We don't know anything about the users, but 71 different requests to the Apache Spark article. Cool. So moving along to the next question, we see here that rather than filter on exactly equal, we use this r-like. Method call here to say, let's look for the Apache regular expression for anything connected to the Apache project. This is probably also a good point to mention this is the first place where we see some of that, or see what makes this $ useful, because in Scala, with Scala strings, we don't have a method .r-like on those string objects, right? So what this $ is doing is saying this is no longer a string here. This is actually a column object that we can then call a few different methods on. So if you like, it would also look like this without the syntactic sugar. And then down below here, we see we do the same thing to sort, and we have been doing this to order by in a descending order. The default is ascending order. So we can see here that in this particular hour, Hadoop was a very popular page. Kind of fun just to see what Apache projects are particularly popular. Cool. So last question. Oh, sure.
Whenever we are dealing with this parquet, it's a column now which is a two-dimensional data set, essentially, right?
Mm-hmm.
But the Wikipedia itself is a graph data. In case if we get ourselves into graph library, we will not need to be going through all this kind of tedious type of common and regular expression type of thing. We could be accessing it as a graph data, right?
Yeah, so there's a question point here, which is that we can think about the Wikipedia data set as a big graph, or that's definitely a very valid view into that data set. And we don't need to think about all this columnar SQL type stuff. And we'll take a look in graph frames at how that actually looks, and how when we start thinking about Wikipedia as a graph, we analyze it that way. So I'm going to kind of hold that question until then. So here, what we're going to do is just calculate the percentage of English articles that were displayed, were requested in a given hour. So the first thing we're going to do is just take a look at our data frame again. So once we do that, we can call a count on this filter data frame to see exactly how many pages were requested in English Wikipedia in the past hour. So you can see here that we have a long object. Again, this is an action, right? So a data frame isn't returned. a Scala object is returned. And in particular, this object is returned back to our driver JVM, or I guess our sort of driver Python environment for the Python users in the room. So once we have this, we can just do a regular old Scala division here, or Python division that's going to run inside of our driver environment, sort of local to us. That's fine, to get that percentage, right? So we know that there are 5.1 million articles in English Wikipedia. So we divide the number that we saw in this hour by that 5.1 million number, multiply it by 100, and we get 24.7%, which surprised me when I was looking through this notebook. In a given hour, 25% of Wikipedia is accessed, and you would, I don't know, I kind of thought that maybe a much smaller fraction, 5 to 10%, would be accessed, but people really, I guess, spread out into the vast breadth of Wikipedia articles in the English language. Cool. So I guess the last thing we'll talk about in this notebook here is some of the SQL functions we can use inside of this data frames API and interface. As we've already seen, this data frames interface looks really similar to SQL, right? Like group by, distinct, order by. All these things are straight from SQL, and that's definitely a design choice. Let's see. But we can see here that on our English Wikipedia, there were, once we sort of do a little hack here, right? Group by project, we know that the project is already just English Wikipedia. And just sum the number of requests that we saw, we see that we served around 7 million people in this hour. And then the next question is if we want to filter for some mobile information. So how can we?
Christian, you have a question?
Oh, sure.
How does it know which columns to sum? Because we have 4 columns. We are using one of them as a group by.
Sure.
Extra column. How does it figure out which to sum up and what not to sum up?
Sure. So it's gonna infer that. So the question is, how does our group by sum here know exactly what to aggregate? See, you can actually see that we did a sum of requests and sum of bytes served. So what it did was it took our number like columns and inferred that, okay, we probably want to sum all of those up, and just did a sum across each of those columns where the schema, in the schema, it made sense to do a sum, right? So we see sum of requests, and again, I guess that byte served information is stripped out of our data set here. But we do get a sum of zeros as well. So that's kind of the inference that's going on there. And I believe in here we can specify the columns that we want summed. We could do sum of $requests. Oh. There are a number of different ways to do that.
If that can just be a string.
Usually I would use the SQL sum function here. Can we just do a sum on the request string? Oh, cool. So it's not as happy with the column here. Sometimes there are some weird inconsistencies with the $. Oh, I guess that kind of makes sense. There's some weird inconsistencies with the $, but you can see here, yeah, we can just specify a request column in this sum function call and be explicit about the column that we care about. Cool. And I think I'm going to leave this desktop versus mobile filtering kind of as an exercise here. But remember, what we're going to want to do is, if you're interested in doing this later, is take a look at those project strings, and we're going to need to do some filtering on the particular project that's being loaded, right? Is it mobile Wikipedia or is it desktop Wikipedia? So that's the way you can kind of go forward and do that one. Okay. Let's see. So we have about 12 minutes before the next break. So let's just start right up on the next notebook of content here. So actually, I kind of want to keep moving. So please feel free to put questions in the document. Again, we have a lot of material to cover today. So I kind of want to keep moving here into a bit deeper of a dive. We just saw some of those API functions and how they look in the data frames, data sets world. Let's go under the hood a little bit, and let's take a look at the Spark UI. What actually is happening when we call an action in terms of the jobs that get run. We're going to look at how data is actually partitioned across our disks and how that relates to the number of tasks that actually get spun up. So we can start, and once we kind of have an understanding of that, we can start thinking about how to optimize. Again, as mentioned before, we'll talk a bit about caching and that really important optimization step. And we'll take a look into some of the query planning that's actually going on inside of the Spark engine when we're using this data frame API, and actually take a look at the specific optimization, some of the specific optimizations that are happening. Okay. So the first thing that we ask you to do here is restart your cluster. I am not going to do that, but would recommend that you do, just so you're in a sort of clean environment. You can do that by clicking up here and attach to. Or excuse me, once you're attached to a cluster, I believe, yep, then you can click Restart Cluster at the top here. Cool. So in this notebook, we're going to kind of move along with that desktop versus mobile partitioning, and kind of dive into, in terms of the analytic questions we're asking, just what's going on there, how we can take a look at sort of days worth of page view data, and in particular some of the metadata on those requests, on that traffic that's actually coming in. So let's take a look at the data set we're looking at here. So you can see here, first of all, here's a bunch of the different data sets that we're gonna care about. What we were just looking at, page counts, so just aggregate traffic numbers. We're gonna look at some of the clickstream data. We're gonna look at that clickstream data as a graph. That's what this GX prefix is. Because I think that stream of clicks is one of the most powerful ways to think about Wikipedia graphically, and so on and so forth. So we're gonna continue looking at that page view data in particular. In particular now, we're kind of, instead of looking at aggregate data, right, we're going to be looking at page views on a much smaller time scale by second. And this is going to be a TSV file. So you can already see we're going to have to think a little bit differently about parsing the data. We can see the specific set of commands that we call in order to load up tabular data here. So you can see we're doing the same spark.read call. We're setting a few options before we actually end up saying load a CSV from this particular location. So of course we change our delimiter to a tab because this is a tab separated file, and load that up. Again, as you can see in the comment here, this was actually a Databricks library in Spark 1.6 that you had to import, and has since been folded into mainstream Spark 2 because it's very nice and clean. But Databricks was the organization kind of doing the development there. The last thing we do in this cell is we're going to actually create a temporary view, page views by second. And what this is going to enable us to do is not just access this data frame as tempdf, but also access it as a table or a view inside of SQL commands that we run. So if we want to basically run the same set of commands or very similar sets of commands to what we'll be looking at, we can do sort of select statements and group by statements in a SQL language. So we'll get to that shortly. Cool. So you can actually see that this command took 27 seconds. So this is kind of the point I was making about Parquet versus other files. So this TSV file is not one that we chunked up. It's not one that has metadata or anything like this. So you can see here that we do have a schema. We have the timestamp. We have the site. And what I can actually do is I won't print the schema, but you can see the schema that we've got going on here. What had to happen was Spark actually had to scan through this file once to see exactly what the data looks like so that it could infer the schema as we asked it to do via this infer schema true option right here. In order to infer that schema, we did have to parse through the file, so it took a bit longer for that process to happen. Sure, this question.
So in the Python version, I see that in the Scala here, you get some idea of the schema. In the Python version, you don't really see that. Is that?
Sorry, the Python version had which thing?
You don't really see any notion of the schema or which columns, even with the Parquet format versus the TSV doesn't.
Oh, interesting. Okay, so in some of the output, maybe we don't see the schema on the Python side is the sort of question that's being asked here. And that maybe it's just a difference in display, but I'm sure the print schema command, I know the print schema command still works, and you can still see the schema that's underlying in the data frame engine there on the Python side. Cool. So there is, just kind of as a point, we can actually look at this same data frame again by pulling it from a table. So show of hands, who here is a Hive sort of person or uses Hive, familiar with it? Cool, so there's a decent number. You could imagine actually connecting into a Hive metastore and Hive table and calling something like this, spark.read.table, for a particular table that we want to load into Spark. The integration there is really nice. So I'll do that now. You'll see this one's very quick. The schema is already there because we've already inferred it and so on and so forth in our first load. So in terms of whether or not this is a transformation or an action, you can kind of see here the subtlety. We are loading this file from disk, and we have to scan some things, and then we get a data frame back. So it's not, in this case, it's not quite a transformation in the strictly lazily evaluated sense. Cool. So then let's materialize some information. That was reasonably quick. We're just showing off the first 10 rows. And an interesting point here is, in all likelihood, in this TSV file, our timestamps are in order. In the case of the show that we just did, these are actually out of order, right? We see 9, 10, but then 19. Oh, maybe not terrible. We definitely, yeah, this is reasonably ordered here. Cool. So now that we've done this, what's actually happening when we call this show command? So this is kind of exciting, right? We see that our show action kicked off some Spark jobs. So again, for me, this is job 53. For you guys, this might be something different. But we can see then, in particular, that job launched a stage. And we can click on the information here. And this is really cool. This is a really easy way to open up actually the Spark UI that you will not just see in Databricks, but you will see in any Spark cluster, or be able to have access to in any Spark cluster that you open up anywhere, right? So you see that here. I can click on this view to get a higher level view of the job. We'll poke around that more in just a minute, but you can kind of see here, in terms of the execution flow of Spark, a job is divided up into stages, and then those stages are broken down into tasks. So if I scroll over here, you can see that 1 out of 1 total tasks succeeded. So as we'll see, probably after the break here, there's some connection between the number of executors we have and the number of partitions that we set up our data in, those two things, as well as the number of tasks that actually get run. And we're going to want to think about that connection to make sure that we're optimizing our jobs correctly based on the number of executors that we have. So again, just kind of introducing this now, and we'll dive a little bit deeper shortly. Cool. So we've all seen print schema, and we can do that here. Cool. So there's sort of an interesting back and forth that happens between Spark SQL and RDDs in terms of some RDDs and data frames or data sets, excuse me, with some serialization and encoding that happens. We'll get into that later, but the point we kind of want to finish up with now is that underlying the data frame API, more or less, is the older RDD API. And in that API, we chunk our data up into partitions. So when Spark loads this into memory, it's going to create a whole bunch of partitions that get sent out to different executors on our cluster, or maybe there are multiple partitions on the same executor. But this data is chunked up into a number of different partitions. So what we do here is we take a look at our data frame, then we say, hey, give me back the underlying RDD. Again, this is the rough way to think about this. Then give me back the partitions and tell me, or some information about the partitions, and tell me how many of those that we have. So you can see here that we have 8 partitions. And the natural question, right, is why 8? We can take a look here at some of our Spark configuration options, and we can see here actually that we have a local Spark running with 8 executors. So by default, we're going to partition our data into 1 partition per executor, right? Which is a fairly reasonable sort of default to have. And we'll talk about some reasons where you might want to have more partitions than you have executors. Typically, you don't want to have fewer partitions than you do executors. And cool. So we'll kind of stop there, and we'll look a little bit more into how those partitions get set up and so on and so forth after the break, which is going to run from now until 11. There's coffee outside. There's bathrooms in either direction. And at 11, there is a parade for a certain football team starting. We're gonna stick to the schedule here and start back up at 11. So see you guys then. Let's get started back up here. I think a couple more people might be still filing in, but we can kind of keep moving here. So first off, we have about an hour before lunch here. So I suspect what we'll be able to do is finish up this notebook. The next notebook is a bunch more sort of data analysis API exposition stuff. We'll try to go through that one a little bit more quickly to move on to the following one, which I think is just a bit more interesting. We'll get through some of that before lunch, finish that up, and then kind of move on into the next section of the day here, which is again more demoing some of the more advanced features rather than looking at this core API. The other thing I wanted to say right now was a ton of questions have come in on the question and answers document. That is great. Please keep those coming in. Keep the TAs in the back busy, and they're responding to everything right as it comes in. Thank you so much, guys, for being on the ball there as well. Cool. So, as a reminder, we are looking at some page view by second data in the Wikipedia dataset here. And in particular, we're talking about Spark internals. What's going on when we actually materialize the data into our data frame? How is that going to look? How is it going to be distributed across our executors and the different partitions? We saw that the default is typically going to be the number of executors we have on our cluster. So this data frame was loaded up into 8 partitions because we have 8 executors in this toy cluster here. So ultimately, in sort of the underlying memory storage that we have here, we see that our data is partitioned up. In this case, there are 4 partitions, but you can imagine this diagram was made maybe when we were doing 4 executor clusters. Now we have 8 executor clusters, so there are going to be 8 of these boxes. Each one represents a partition. And then some chunk of the data is sitting in each of those partitions as kind of an independent fragment, right? And in particular, when we load up this TSV file, we are going to have to send that data out to the different partitions because it is not in a nice chunked format already for us, right? So as that chunk size comes in, or as those chunks of data come in, we send them to different partitions, and so there's a point above about stuff being out of order. Sometimes in our partitioning step, data can be loaded into different partitions out of order. Just a side point there to think about. But yeah, this is kind of the high level structure here. So what does that translate to when we actually start performing actions and running jobs? Well, let's look at one of the simplest actions we can take that's going to trigger some jobs, a count, and think about how that's going to look. So we'll give this a second to run. And so we can see here we have, what is that, 7.2 million rows. And zooming in again, looking at this job view, okay, my job's 57, your job has a different number. We expand that and we see that we now actually have 2 stages in this job, which is interesting because again, a job is sort of broken down into stages depending on the logical steps we can compute at each stage. And you can see here that this first stage has 8 tasks. So can anyone take a guess as to what those 8 tasks are corresponding to? Partitions, exactly. So I think there's a diagram down here that I'll sort of scroll down to before we take a look at the Spark UI. What's happening, right, is on each of our, here you see a diagram of 4 partitions. We have 8. On each of those 8 partitions, right, a local count is running, which is going to then end up with one final count for each of the number of rows in each of our partitions. Then we send that final count out to as one final task to one final executor to say, okay, sum up the 8 different values that we got and give us back our final count, right? So at a high level, that's what's happening with the algorithm here. And so that's exactly what we see when we say, okay, this is all the way back up. Divided into 8 stages here, or excuse me, this first stage is divided into 8 tasks. We then do a shuffle step. So anybody who's done MapReduce stuff before, that shuffle step is always the network IO step, right? So here in this case, the shuffle step is sending those aggregate counts to one particular executor, and then aggregating those. So without further ado there, let's take a look at the Spark UI and see how this kind of breaks down in there. So you can do that as I just did. I will rehash that again. You click on your cluster in the top left corner, and there's going to be an option to view Spark UI. You can just click on that, and it's going to open up a new tab just like it did for me. Cool. So you can see in here, we have a whole list of jobs, all the jobs that I've run so far. So you can see where those numerical IDs are coming from. They're just kind of incrementing. And then you can see some description information. So here in particular, here's the count action I just called that triggered this whole job to run. You can see when I click that button, you can see how long it took, and you can see how many stages were required. There, you can also see that in total we had 9 tasks run, right? 8 plus 1, and that's shown for us here. So then we can drill down a little bit if we click into this link here. And we can see then our 2 respective stages. And interesting, we don't see the input here as maybe we'd expect to because we're reading in this data from S3, but typically in the Spark UI, you'll be able to see that could be because I'd run this before and didn't restart my cluster. You will see that it would be here in this first set of 8 tasks, a bunch of data being input, right, and loaded in. And that's in the diagram in the previous notebook. Then in we also see kind of an interesting I/O point here, right? Shuffle right, it's 472 bytes. So what is that corresponding to? That's corresponding to the 8 final results that we need to send over the network into one executor, right, to be aggregated. So then on the other side, in our final aggregation task here, we see that that those 472 bytes were consequently read in by that for that task, right? So you can see the first count took about 8 seconds, and then we had a really quick final aggregation happen. Another kind of cool visualization you can look at here is actually the flow. So we'll poke into this more, but you can kind of see a cool graph of the different steps that the Spark Query Planner has broken this down into. And you can see here that we kind of have this these 2 different points between our stages, where this is the first aggregation, then there's this transfer across the network, and we continue on. Then we can, this is sort of not the best way of looking at this, but we also have a whole bunch of other options at the top of our Spark UI here that we'll poke around a little bit more. We're going to be interested in the storage one in the near future for some caching concerns. But again, we can kind of drill down into particular tasks and see exactly what was going on. Oops. There. So we can see where each of those, there it is, where each of these tasks ran. Again, these are local processes, but you'd be able to see the IP of the particular machine and the sort of information. All here, how long each of those tasks took, whether there were successes or failures, did we have to retry any tasks, all these things that you kind of worry about. So this is all kind of nicely in the Spark UI, and we'll keep looking at that throughout the day. Cool. So, yep, again, breaking it down. If you want to look at this later, you can kind of go back through everything I just said pretty easily. Just follow the really nice outline we've got here in the notebook. And as I mentioned, you can see here, I think some kind of local caching might have happened where I did not see this initial 250 megabytes of input loaded up, but that should be there so that we can then see the chunking that kind of happens in the tasks. Cool. So yeah, I guess one last thing I didn't point out here in the UI is when we take a look at the final task here, we can see that this number of records that's coming in is after the slash, so we can see the 4 records were coming in and how big that size was. So if we look at that in the Spark UI over here for that second stage, and the one task that got generated from it. We can see there that for us, because we have 8 partitions, there are 8 records coming in, and we have 472 bytes of data total. Cool. So, in the previous notebook, we started looking at order by. So again, we're gonna sort by timestamp here. To get our data strictly sorted in order on a per second basis. So you can see already, and if you guys follow along and actually execute this cell as well, that this is going to take a bit of time. There it goes. You can, either from the Databricks UI or from the Spark Web UI, actually keep track of what's going on live inside of jobs, which is kind of cool. So you can see how things are progressing right inside of the Spark UI. So you can see there that our order by took one stage with 8 tasks. The idea here is going to be similar to merge sort, where we're sorting our partitions and then pulling back records as needed from each of those partitions. In any event, you can see here that we have a, a useful command is, or another useful parameter you can pass into the page views df is truncate equals false. Oops. And note that because we haven't cached anything yet, this is something we were talking about earlier. This is going to take quite a while again because that data frame is in fact rematerializing. There was a question from over there about that earlier. So all this truncate equals false call is doing is saying, hey, give me the entirety of these timestamps. So you can see that for each second here, we have 2 records. We have a mobile view and a desktop, or a number of mobile requests incoming and a number of desktop requests incoming. And you can see that because we only sorted by, or ordered by the timestamp field, those come in out of order in certain instances, right? We see here the first one's mobile, second one's desktop, but at the 1 second mark, first one's desktop, second one's mobile. So of course we can extend our order by query so that things are consistent. And we can do that quite easily with a call like this. And in particular, again, as from before, we're using that .desc function for a descending order, somewhat arbitrarily. Hmm?
So what the truncate function is?
Sure. So there's a question about that truncate parameter. If you try running the cell without this truncate equals false parameter, this at the end of the timestamps will be truncated into just like ellipses. So it's just nice to be able to see the whole thing, kind of useful thing to do, that's all. Yeah, heading back down, you can see this is starting to take some time, right? This one took a full another 20 seconds. So let's start thinking about how we can cache. So even though at this point we've made several calls onto this page view df, right? We've taken some rows from it to display them to ourselves. We've run this count command at least once or twice now. It's still taking a bit of time. It still took 6 seconds to run that count. And the reason for that is because each time we currently call an action on this data frame, again, this lazy evaluation this lazy evaluation is happening, and that data frame is being rematerialized from disk every single time. So how can we get around that? Quite easily here. And 20 seconds, I guess our executors are slightly faster, by using this .cache call. So again, this is a transformation. It's lazy. We're not going to cache anything until we load it up. But once we have that data loaded into memory, we're not going to evict it from memory. We're not going to reload from disk. We're going to use the cached data frame that we have in memory. So this is one particular way of caching the caching the table. But as I was kind of showing earlier, there are a number of different ways to do that. We can just call it .cache right on our data frame as we're moving through our as we're moving through our execution flow. So in this case, I'm again calling count. This is the first time that we've had this table cached, this data frame cached. Or we've said, this is the first time at least that we've said, hey, I want this cached, right? So you can see here already that this count action is taking longer because not only is it counting up all the data, counting up everything that we're pulling in from disk, but it's also storing it in memory so that it can be used later. So just to demonstrate, now that we have used that cache sort of quasi-transformation, this time it only takes 0.2 of a second, so big increase. So the next sort of question is, can we take a look at the memory that we're actually using for data frames? We're caching, right? We want to make sure that we are caching information we care about and not caching too much, right? So we appropriately utilize our memory without evicting things that we might care to use later. So there's a pretty easy way to do that, again, in the Spark UI. If you close that out, again, it's top left, view Spark UI. I've got the tab still open. And if I click into the storage tab right here, I can see that we have this whole, again, remember the thing underlying data frames, the structure is still RDDs. We can see here that we can actually see that full RDD sitting as 8 cache partitions in our memory. 100% of it is cached, and notably, it's only 89.5 megabytes. So there's actually some compression that data frames are doing, and some tricks with memory storage, like off-heap memory storage stuff, that allow us to substantially reduce the size of our fields. If you think about how big Java objects are and the overhead that's there, basically Spark 2 in particular, but the data frames API is doing a bunch of stuff to compress that down and not use strict Java objects, keep our data a little bit smaller, better compressed. And we see the storage benefits of that here versus the couple hundred megabytes of memory that get loaded in every time we load up the full string data, right? So we can see here, we could see if we had a full cluster, where that data would be partition 2 on all the nodes and where the particular, partitions were living. Here they're all in the same place, and then we can see how those partitions are broken down by size, and the size in memory of each of those partitions, which is going to be different than the sort of full size that we're loading in, right? Cool. Yeah, so that format I'm alluding to is the tungsten binary format. Again, that's a low-level thing on the data frames. If you want to learn more, I think there's a bunch of resources at the end of this notebook or in a couple other notebooks, but tungsten binary format is kind of what you want to be searching around for in terms of the specific format data frames we're using. But you want to think about that, again, as an underlying RDD, rather than worrying too much about those particular implementation details. Yes, question?
So you did the .cache command on the Spark table,
Mm-hmm.
not the page views DF.
Yes, so the question, so the question is, I called the cache command up here on the spark.table. That is not necessary. I could do pageviews.df.cache.count, and that is going to do the exact same thing.
But in that case, you have to make sure that you call count as an action following cache.
Yeah, so the question is, do I have to call count as an action following cache? And in either case, the answer to that is yes. Regardless of whether I do the table or the data frame, it doesn't matter which of those two objects I call this cache transformation on.
Cache on the page views DF, and then that second time we called count would have been faster. In this case where you have it right here, is that just
Sure.
one instance?
Yeah, so the question is then, what happens here when we cache again? And let's take a look. It's going to be really fast because it's already cached, right? So the recache, is that what you mean? The recaching doesn't happen again. Spark is sort of smart enough to know that.
I'm a little confused why you didn't have to assign the value from the caching on the table to something. It seemed like it sort of stuck to the table. Where cache is returning another data.
Yeah.
You do it on the data, but not on the table.
Yep, so this is a question about what's going on with cache in particular. And so again, this is a transformation, but with side effects, right? The side effects are we're going to earmark this to be cached in the future, but we don't need to particularly use the cache data frame that gets returned there. So it's
So it gets kind of attached to the data frame?
Exactly.
You don't need to use the result of that cache function as the data frame?
Exactly, yep. We could just keep, once we call this cache transformation thingy somewhere, we can just keep using pageviews.df and it will be cached in the future. Again, after we call an action, right? After we call a count or something like this.
So any action you run on the data frame will be faster after you use cache?
Yes, so the question is, any action you run on the data frame will be faster after you use cache? Yes, almost certainly, because it's in memory, right? We don't have to reload it from disk for every action that we call and every set of jobs that we trigger from that action. Cool. So now that we've done that, we can do some of these filters and counts. You'll see that these run really quickly. So the first question here is how many page views were coming in from mobile, and we see that that's, or excuse me, how many rows of mobile data do we have? We see that exactly half is mobile data. Because again, at every second step, we have one mobile, one desktop, right? So that's That's pretty expected. And if we open up the Spark UI, we'll see we can take a look at all these time take, number of stages questions again, and we'll see that it is in fact quite similar. I'll let you guys poke around that for yourselves and see how it is in fact a lot faster and what steps are being skipped, namely the loading from disk steps, right? Those steps are being skipped in the Spark UI when we call this count again. Kind of cool. Cool. So if we want to know how many rows refer to desktop, well, we kind of already know that it's exactly half again, but we can just copy the above. And again, using this filter call, say site equals desktop. And this is going to take a quick second. Again, exactly half of the 7.2 million. Cool. So there was a question about this earlier, which is basically we're calling a transformation here, right? We have our data frame, and then we call filter. That's a transformation that's going to give us another data frame. And then we call the count action. Does that mean that this first data frame is materialized? Then the filter data frame is a separate thing that gets created in memory? And the answer is no. We have a bunch of underlying lower level optimizations that are happening, right, and query planning that's going on that's going to make that faster. We call those two separate things the sort of logical plan, which is our understanding of how these data frames are transforming one to the next, versus the physical model, which is going to be that low level optimized thing that is not going to be separate data frames. But instead, something more along these lines, right? 4 counts on local machines, 4 counts on 4 different executors that get sent to one final task to one final executor. And in particular, I think it's time to take a look at how this physical model kind of looks under the hood. We do something called pipelining here, right? So the idea is what we can do is when we are either loading up our data from memory or from some other data source, like, for example, Parquet that's columnar, and allows us to actually filter while loading data in, we can allow Spark and its optimization and its nice sort of physical level optimizations to say, okay, on this partition over here, do the filter and the count locally. On this partition, do the same thing, just as one step, as one stage, because we don't need to do a shuffle until that very final point when we send all of our local counts to the final executor, right? So again, what's actually happening under the hood is going to look a little bit different than the way we think about it, but it is kind of like if you spend a minute thinking about how would you optimize this, Spark is kind of doing it that way, right? With this notion of pipelining. So let's take a look at what that query plan looks like. So when we do our filter count here again for the desktop site, what we can do is go back over to the Spark UI and click on SQL. And you'll see here there's a couple of like show tables things that happen on our local driver. We're not as concerned about those. I think these are actually commands that are being run to show the Spark UI to us. But look at that, the count command right there is what we really care about, right? And we get this nice diagram of what the query plan is going to look like. So the first thing we do is this in-memory table scan to look at the table as it's sitting in memory, right? Because we've cached it. So we just have to look back into memory rather than loading from disk. Then in one single stage, we filter down, and this project call is basically saying filter out all the other data and get rid of it because we don't care about it right now. And once we do that, we do this aggregate step. This exchange is going to be, we're going to see this a bunch. That's the shuffle step into our second stage. where the final aggregation happens. Notably here, there's this kind of wrapper box, which is saying whole stage code gen. For Spark 1.6 people, if you've ever taken a look at this UI before, you'll know that this wasn't here. This is a new Spark 2.0 feature that's basically saying, as it turns out, it's way faster if we generate all of the Scala code that we're going to need here as one kind of really long auto-generated thing. That, again, speeds up execution dramatically for our stage. So there's this kind of pipelining whole stage generation step that happens in Spark 2 that makes things way faster. Later in the afternoon, maybe we can take a look and see when we turn off this whole stage code gen optimization, how much slower things get, but it's a big improvement. Yeah, there's a question? Or? So you're, okay, sure. I would say grab a TA for that particular question about not being able to see the tables. I think typically you're going to see a lot of show tables if you poke around the UI is sort of the problem because of all the UI commands that happen. And you have to kind of scroll down to find that count for the last time that you've run it. So that's kind of always the subtlety with looking at this SQL tab is these show tables commands actually get logged into our UI, even though we don't necessarily care about them so much. That being said, there is another easy way to take a look at kind of what's going on in terms of our physical plan versus the logical plan that we think about. And if we scroll down, so you can see that in the SQL UI, but I'd rather just show it to you here. What we can actually do is explain what the query plan is going to be. So you can do this, again, in Databricks, in the Spark UI, or just in a Spark shell as you're working to see kind of what's going on. But it's, I think, mostly useful for instructional purposes. We can call .explainTrue on this filter transformation, and we can explain exactly how we got to this point in the data frame, right? So you can see here, there are a bunch of different steps. First of all, we're parsing out our logical plan. So what we're going to do there is just figure out, OK, we've got a filter, and so on and so forth. Not super interesting. Then there's some analysis that happens. And then we get down to the optimized and the optimized logical plan and the physical plan. The optimized logical plan isn't going to be too interesting for us quite yet. But the physical plan is really interesting, right? Because what's actually happened here is we, first of all, Spark has added another filter for us, right? We care that we're not looking for null rows, so that's some sort of physical optimization that needs to happen, or lower level optimization. And then number two, that our site is equal to, the values in our site column that are equal to desktop, right? And then actually from there, we just we scan, as we're loading up information from memory to be worked upon, all we're loading up is the rows where site equals desktop. So we kind of push that filter down to the memory level. So that's kind of cool and useful to know about. Cool. Any other questions there? We don't have too much time. Great. Yeah. So takeaway there: Spark is very fast, and is smart. Cool. So, kind of moving along, we want to start thinking about partition optimization, right? So, let's think about how some repartitioning might work based on the particular structure of our EC2 cluster. So in this case, we have this local mode executor that's running, or excuse me, we have this local mode Spark session, or yes, in Spark 2 it's the Spark session, a local mode Spark session that's running with 8 executor JVMs in local mode, right? As it turns out, on EC2, we have actually 3 sort of slots that we can execute on. So given that, we might actually think about sort of rearranging our partitions, right? Right now we have 8. Maybe we want some multiple of 3, right? So that we can say at any given time, in each slot we have, if we do 6, for example, we have 2 partitions waiting to be worked upon, right? And then somehow there's some nice even distribution there, and things might work a little bit faster. So let's try that out and actually see how it goes. So the first thing we do is unpersist. So this is going to be a call. If you ever want to manually evict stuff from cache, you can call this unpersist. Again, kind of transformation with side effects. And if we look now that I've made this call in the storage tab in the Spark UI, we're going to see that it's empty, right? I just said, hey, evict that from the cache. We don't need it in memory anymore. So now what we can do is oh, okay, cool. So now what we can do is the first thing we want to do here is reorder it and take a look at something else that happens that's kind of interesting. So first of all, I guess, what we can do is repartition, I believe. Yep. We can make this repartition call to say, when we load this up, partition it into 6 partitions. And then we're going to order by, timestamp, and then $site.descending. Then we're going to cache. And I'm not exactly sure what's holding this up here. Repartition is a transformation usually. Thank you. Yes. So I'll just alias that down here. Val page views ordered df equals page views df. Cool. Okay. Oh, I think it's because we had to look back at disk to see what was going on again, unfortunately. But then now let's actually materialize the full cache. There was some scanning of our disk data because we're sort of repartitioning here, but then this time our count is a bit faster. So we look in here at our Spark UI, and we're going to see that there are still 8 tasks. That's strange. There should have been There should have been 6 tasks there. Okay, I'm gonna come back to that and have a correct answer for why this repartition didn't happen exactly the way we expected it to. Oh, okay, no, I'm sorry. That's because the repartition step does actually spin up a job. So repartition is again kind of one of those weird quasi transformation action things that is not lazy. So then we can see here we get 6 partitions after that repartitioning step. And then I did not save that off. Yes, so we'll do that again. Cool, so now there are a bunch of stages that are gonna happen. First of all, we're making sure to repartition, save that off as page views order df along with a cache with one skip stage because we kind of already had that before. So this is where it gets really interesting, right? And first of all, you can see we have a few stages going on in our job. First of all, we have the repartition stage. Then we have a stage here that has 200 tasks going on. And the final stage then is going to be just the aggregation that we expect. But kind of the question here is, so we did our repartition as an optimization, great. But then when we did this order by, why do we then go to 200 partitions instead of the 6 that we had? Which step did that? And you're probably guessing it was the order by step. And we can see here that we're kind of still in 200 partitions. The reason for that, again, is this order by step. And the particular configuration variable that is setting that is this spark.sql.shuffle.partitions variable. Basically, our order by step is going to require, once we actually want to fully materialize this data frame in an ordered row of partitions, we're going to have to do a bunch of shuffling after we do our local sorting, right, to get everything in the correct partition. And there's a whole bunch of like distributed sort problems sort of associated with that, and a bunch of cool work that's been done there. But in any event, the default number here of partitions is set by Spark to 200. That currently is not intelligently set. It's reasonable for a bigger cluster, right? I think that was the reason that default was chosen. For a non-trivial cluster, 200 partitions is a default number that kind of makes sense for if we do have a bunch of executors on separate machines, right? However, in this world, those 200 partitions really just chunk up the data in a way that we don't care about, and that slows things down too much. So let's go back to 8 partitions because we have 8 threads running in our local Spark thing. So again, the number of threads is different than the number of slots on the EC2 cluster. So we have 8 cores, we typically call them running, but 3 slots. So what we can do is use this spark.conf.set call to say, okay, rather than the 200 that's the default, we're working in a much smaller cluster environment. So let's use 8 partitions instead. So this is kind of the process that you go through when you're thinking about how am I going to optimally partition my data, and what particular configuration variables do I need to set. The spark.sql.shuffle partitions is an important one, and then explicitly repartitioning in the beginning can be really helpful for later on. And the question?
So in a shared environment where we are uncertain of the number of executors our job may get at runtime, is there any way to manage this number?
In this local community edition mode, no, there is not. We're kind of given the Spark environment and just work with it. Yep, question here.
What about in AWS where you have options like maximize resources and stuff? Does that affect these sorts of options?
On EMR, I'm not 100% sure which ones you're referring to. I would put that into the document, and we can go from there on that one. In terms of EMR, you're typically setting the number of nodes you have, right? And then you're going to have to do Spark configuration to say how many executors you want in each of those nodes.
You've got this option in EMR of maximize resources, which attempts to do this calculations on the
Oh, okay. Yeah, put something in the document, and we can figure out exactly how that's interacting. Cool. So now that we've gotten a reasonable shuffle partitioning and a reasonable kind of initial data partitioning, let's see how much faster things are when we unpersist this. And just starting from the base, loading from this table, and doing a shuffle. That's going to be sorted. Because we're reloading from this page views by second sort of base table that we set up way above, we go back to still 8 partitions because that sort step is now just using 8 of those, which is kind of nice. Oops, we can see the visualization here. we can see the visualization and the exchange that's happening in this stage for that sort operation. And then last but not least, so this is another interesting point from the Spark UI that I think is worth showing off. So we have this live count job running, right? And so far it's been running for 22 seconds. I'm over in the Spark UI now. You can see here that this particular step, this map partitions internal step, actually has a green dot. And what that's telling us is that some kind of internal caching has actually, because the dot is green, some kind of internal caching had already happened here. And you can kind of see that when you poke in, we're actually loading this up from the cache. And then from there, we proceed with the rest of our count job here. So we come back, and it took a little while, but we got the count done. Okay, so I changed things up a bit here, so this is not going to reflect exactly, I think, that repartitioning is not going to happen explicitly again. But we are back to a world because of that shuffle, because of the shuffle configuration that I did explicitly set, where we have eight partitions at the end of all that cache materialization. Cool. And then we can take a look into the Spark UI and see those 8 partitions again, but it's going to be exactly the same as before. All right, so we've got about 15 minutes. So this notebook is going to be really quick. This is just going to be some more useful commands we can do in the Spark API, thinking about once we cache things, how we can look at data frames, and a quick intro to joining data frames. But again, we're going to look at that in the future. So click over to this notebook number 3. And now that we know that we don't want, whenever we do an order by, for 200 partitions to be created, especially if we materialize the full thing, as we do when we call a count or something, we want to set that number of shuffle partitions to just be 8, so things go a little bit faster. Okay, we're looking at the raw page use data just as before. So when we were calling that spark.read with the infer schema equals true, I mentioned that we were inferring the schema, right, by having to scan the file. So let's suppose that we don't want to scan the file upon that first spark.read. And this is a bit cheap because we are actually showing some of the data here by doing the spark.read.text. But in any event, what we can do as people who do not necessarily want Spark to infer that and have to scan over the data set once for us, is we can actually construct a schema ourselves and pass that in and say, hey, Spark, use this schema and no need to infer, right? This is what the data is going to look like. So we can start out that process by just taking a look at the raw data. We can see that here. Timestamp, site, and requests we have that first header column. And then looks like timestamp is going to be a timestamp, what is this, a UTC formatted string. Then a string, and number of requests is going to be an integer. So we can use that information and a couple of calls along the lines of the ones in this cell. So we import the SQL types from Apache Spark, and that's going to look really similar in Python. And we can actually construct this struct type and then pass in a list of the different fields that we're going to see. So we're going to see before we try to parse this timestamp out as a timestamp, there's a little bit of trickery that goes on there. We first just load it up as a string. We do the same for the site field that we're pulling in. And then last but not least, the number of requests is going to be an integer, right? Because we can just immediately parse that out when we load this up. The true here is, again, that nullable field we were looking at. So we do say, yes, columns here can be nullable, and that should not throw any kind of exception. So we can run that. And from there, we have a bit of a hack. This is, I think, a really useful one. If you're looking at any kind of time series related data, you're probably going to find yourself in a situation where you need to think about parsing timestamps. You could do that with the following little code bit. So just parsing through this, we see that we are doing spark.read. We're setting our delimiter to be tabs, because again, this is that TSV file we were looking at. We set the header to be true. We choose a particular schema. So this is the first different thing, right? We're saying rather than infer schema true, we're saying use this schema and go with it. Assume that the data matches this format and coerce those types. Then from there, we say, okay, this is the file that I'm going to be looking at. So at this point, we have a data frame. After these lines right here that I've just highlighted, we have a data frame, right? From there, we can then chain calls onto that data frame, which we do here. So we're selecting from there site. We're selecting requests, which we already have. And then I think the point of this select statement is to highlight this Unix timestamp Spark SQL function that gets called in. Again, we're doing that import statement right there. This Unix timestamp Spark SQL function that's saying, okay, take this timestamp field, use this as the parse string. So that's the first thing we do. So that's going to give us back a timestamp number of seconds since January 1st, 1970, right? The epoch timestamp. And something that Spark does know how to do, and this is kind of just one of those tricks that you have to know, right? What Spark can do is actually cast that into a timestamp type. So that's what this .cast timestamp is doing. And then we are doing a .as, which is an alias call. So we're aliasing back this whole set of functions back to the timestamp field name. And we do that, and then we have nice timestamp types that we can work with kind of in the way that we'd expect, rather than trying to worry about either seconds since 1970 or string, whole messiness with strings. So again, we show off how that ends up looking. And we can see that also our columns have now been ordered in the particular way that we wanted them to be ordered in, site, request, and timestamp based on the select statement that we did above. And the timestamp looks good here.
Why is it missing its fraction? They're all zero.
Yes, so the question is, why is it missing its fraction? You can actually see here that we're just parsing out year, month, day, hour, minute, second. So that's not something we're parsing in.
Right, but when I try to add like a .s to that,
I am not 100% sure. I guess I would, apparently if you do try to add in that extra format point, you don't see, oh, well, it looks like the data that we're loading in doesn't have that either. So that might be why it's not loading in. But again, feel free to put something on the doc for that. Cool. So now that we've done a bit of typecasting, we can print out the schema and see that we actually have now a different one, right? Site's still string, request is an integer. Timestamp, rather than being a string like we'd initially specified, is now a timestamp. And that allows us to do ordering very easily. So once we've gotten our timestamp type, ordering by timestamp is a much easier thing to do. So we're just kind of doing the same thing that we did before. Again, we're creating this view for the future ability. The reason we keep running the cell is for the future ability to run SQL commands rather than doing it in the data frames API. Yes, the question is what's going on with the different types up here. So that's what's going on in this final select statement here. We're also, when we do the select, calling a bunch of SQL statements, so we're saying take the Unix timestamp, or excuse me, call the Unix timestamp function on this string field, which does recognize the ISO format that these strings are in, because we can pass in a format string. So from there, once you have that, you can actually cast that into a timestamp type. So that's what this .cast call is doing. And then from there, we're just aliasing the name back to timestamp.
I got that, but I'm still confused about the part when he specifically said that to take it as a string type, then why is it why the schema is still showing up when we have specified the schema as a string type?
Oh, sure. So the question is like how do we get from this schema to the one we see below? And the answer is right. So if we were to get rid of this select statement and look at this data frame, that's going to be something that's going to have the schema that we initially explicitly said, right? So this all here is one data frame that's going to have this schema, and then when we do the select statement, we are changing the schema. We're implicitly changing the schema by saying cast this to a timestamp type, right? So Spark takes care of that right there. And it's because it's this whole chain of calls.
How good is Spark at inferring the schema?
How good is Spark at inferring the schema? Typically, quite good in my experience. I've been able to work with a whole bunch of different data types, and then for schema equals true works well. Sometimes it will not get the nullable equals true false correct, so that's one thing to look out for. But for the most part, it's quite good.
Would it have actually figured out that this would be a timestamp?
Would it have inferred this would be a timestamp? Not 100% on that. TAs, do you guys know, would that have inferred the timestamp? I don't think it would have, which is why we're kind of going through this exercise.
I think we can test out some basic formats and then see if those work.
Mm-hmm.
And then basically based off of that. But,
Yep. Yeah, so
I often like use the schema, so I use it for the schemas from the type it all, and
yes. Yeah, so a little discussion going on here. There is a great trick, though, which is when you print out the schema, you can kind of you can start with a scan and see what Spark infers, and then go from there to explicitly specify, okay, I do want null to be true or false, or any other sort of changes you need to make, right? So you can always see what Spark's inferring by a quick scan of some portion of your data, just a small exploratory load up there, right? And then go from there for your production job to make sure that you're specifying the right schema.
Could it also infer like Unicode format?
Yes, I believe Spark is good at the Unicode string type thing. I think I'm going to, in the interest of time here, we only have a couple of minutes, defer any further questions to the document. TAs have been really on the ball with that, and they will be super helpful. Cool. So we did the cache, and if we were to look back in the Spark UI, we'd see that again. So yeah, I think what we want to show off here is just a couple points that we're going to keep working with throughout the rest of the afternoon. So it's not too bad that we only have a couple minutes to finish this up here. But first of all, we see that rather than using a .sum call at the end, which is an action, or excuse me, a transformation that we can only take on group by objects, what we're doing here is saying sum up the request column. So this is the Spark SQL function that gets imported. And again, this is going to look really similar to anyone who's written SQL before. I know on the survey we had a bunch of SQL pros, which is why I'm trying to kind of explain it in that way. But you can see here we're calling the sum function on the request column and then selecting that, right? So again, just like a sort of SQL statement there. And we get the total number of requests that this data frame is logging. And it looks like there are, what, 13 billion, 133 billion? There are a lot of requests. Yeah, 13.3 billion. So I will leave these challenges, again, kind of as exercises, but you can use those filter calls that we've been talking about to take care of that. Now that we do have the data in a timestamp type, we can use this year SQL function to say, hey, extract the year from that, which is kind of nice. So we can just select the year out and to get the distinct number of years. We can do similarly for months. So we can get the distinct number of months that are showed in this data set. And you can kind of guess if we're using the year function here, you might want to use the month function for a challenge like this, right? And that's all explained in the Spark API documentation. There are a few other ones we can work with: week of year, day of year, that kind of thing. And then from there, again, there are a whole bunch more Spark SQL functions. The key takeaway here is that all of these SQL functions, to be used as you typically use SQL functions, are outlined in the Spark API documents. So as you're thinking about exactly what you need to do, you can work through here and see, okay, there's an average function I can call in my columns. So if I want to do an average, I can do it that way. There's all sorts of windowing stuff, and we'll talk about some actually timestamp windowing we can do as well. But it's all here. Let's see. And I do not want to hold you guys up from going to lunch. That would be not great. So the last thing I think I want to point out here is user-defined functions. Yeah, and then from there we have a bunch of sort of Databricks specific visualization stuff, which is all really cool, and I'd recommend you looking through, but is not sort of the core point here. So let's talk about user-defined functions. Basically, what we can do, as you can in Hive or in other SQL things, you can write your own functions, right? And so in particular here, what we're trying to do is say, if we have a date formatted string Monday, let's add a number to the front of it so that we can then sort those days of the week more easily. You really don't need to do this, or excuse me, you really don't need a UDF to do this particular thing, but it's useful for instructive purposes. So we can kind of write up that function, quickly unit test that indeed upon seeing Tuesday, we get back 2-2. I have scrolled through a bunch of stuff, so this will not run, but I don't think that's the hugest deal. But you can see here that we are saying, in order to take this function and register it, we call spark.udf.register. We're going to call this function prepend number. And we're saying pass in the function object. That's what this underscore is doing in Scala. And it looks fairly similar in Python. We just don't use the parentheses, right? But we pass in this function map day of week that we wrote above as the actual function that should be registered as a UDF. And then we can use it ultimately via this prepend number UDF function call, which is really nice. And that's going to be present. That's going to be serialized out to all of our executors as Java bytecode and run on all those executors. So the nice thing about this, obviously, is we can write arbitrary code to act on our columns, right? The not so nice thing about it is that it's Java code. So we might be able to optimize, or the Spark engine might be able to optimize how it does its built-in SQL functions, right? It might be able to do a quick average or things like this. With user-defined functions that we write, Spark is not going to be able to look at your Java code and say, oh, we could optimize it this way. Or this function is actually built up of these other base functions, so we can do this in a faster way, right? So user-defined functions are something you want to avoid because we are not allowing the Spark engine to optimize for us. But they are a very useful tool to have when you can't do what you want to do with just the SQL commands or the SQL functions that live by default in the Spark API. So with that all said, it is 12:03. I've kept you 3 minutes late. I'm sorry. It's lunchtime. Lunch is on this floor, I believe, around the corner. And we will reconvene back here at 1:03.